Hi everyone, and welcome to my presentation of my Capstone project, which has been about predicting heart attacks with machine learning. So first of all, I want to introduce the dataset to all of you. The dataset consists of about 300 records of patients. It's a labeled dataset, and it contains, among other, these features. So age, the subject's age, their gender, if they have been experiencing certain types of chest pain, their resting blood pressure, and so on. And I also want to highlight the label of this dataset, which is a binary label that indicates whether the patient has a high or low likelihood of experiencing a heart attack in the near future. So this dataset is really interesting, but what can we do with it? Well, consider this. Annie, 54 years old, visits a hospital for her yearly health checkup. She is received by her family doctor, who proceeds to take measurements as blood pressure, cholesterol, and the doctor also asks questions related to how Annie has been feeling lately, if she's been experiencing certain pains, etc. The doctor fills out the answers that Annie tells the doctor into a form on her computer, and the IoT devices that she's using to take the measurements automatically fill in their values into the form as well. And when everything is filled in, she submits the form, and within a second, a machine learning model deployed on the cloud has determined whether Annie has a higher risk of having a heart attack or not. This, I believe, is extremely interesting, since it could potentially save lives if it works accurately enough. And it could also be a use case that could be used at home if the patient is willing to make the measurements and fill in a form on his or her mobile phone, and if they have the measurement tools available at home, of course. So over to my solution for this use case. Well, I have evaluated several machine learning models, including deep neural networks and other machine learning models. And from my evaluation, I have come to the conclusion that the best performing model in terms of sheer accuracy has been the support vector machine, specifically a support vector machine with a polynomial kernel. And this model has achieved a test accuracy of 83%, which, given the small size of the data, is very good. And I have also implemented this in a way that the model is deployed onto a server, which means that predictions can be requested via computers and phones via HTTP post requests, which means that the model can be on the cloud and be used for predictions anywhere, anytime. So now I want to go over the technical details of my project. First of all, to the architectural choices. Well, my primary focus has been to have a model that's as accurate as possible, since this could mean the difference between life and death. And the model should also be able to handle a lot of requests, since a lot of users might use the model at the same time, which means that it needs to be fast as well. And the model should potentially be able to reside inside Internet of Things devices, given that some patients or doctors might not have access to the internet while using them. So therefore, a lightweight model is desirable. This problem is a binary classification task, and this means that we know that some models should perform well. And this leads to that I have decided to evaluate neural networks, support vector machines, logistic regression, as well as decision trees. And I have decided for the deployment part to deploy the model onto a Flask server. The reason for this is that, first of all, well, it's simple, since I have used Python for my model programming. It means that the model is in the same language as the server, since Flask is a Python framework. And the second reason is that a Flask server can still be used in production, even though Flask is a lightweight framework. And the Flask server can be scaled with some configurations, which could be really useful if we decide to scale this model to the whole world, for instance. And when it comes to programming language, I have decided to use Python since it's a powerful language and provides a lot of useful tools and libraries for this task. For instance, for the deep learning part, I've used PyTorch. And the reason for this is mainly that I'm familiar with the framework, but also that it offers flexibility in terms of fine-tuning the nitty-gritty details of the model. And it also is a high-performance library, and since it's possible to save the models trained in PyTorch in different formats, it's easy to deploy the models onto the cloud. For data processing manipulation, I've, among other libraries, used Pandas and NumPy, which are really powerful libraries that have helped me a lot. And for data visualization, I mainly used Matplotlib, which is an amazing tool for visualizing model performance over time, but also visualizing the data during my exploratory analysis of the dataset. Lastly, I've also used scikit-learn, which is a really good all-round library for machine learning, since it allows for model evaluation, such as cross-validation inbuilt as functions. It allows for training the data, or rather splitting the data into training and test sets. And it provides a lot of good machine learning models out of the box, which I've used. And it's also worth noting that it's really easy to save models built in scikit-learn as well. So now over to the ETL process and the feature engineering process. Well, first of all, I downloaded a dataset, and I want to mention that the dataset comes from Kaggle. And it's also worth noting that since the model is deployed online, data could theoretically be added and trained on via HTTP requests even after the model has been deployed. So this means that we can continue to improve performance of the model, which is of course really important, and we might be able to achieve a better performance once patients start using this service. And as I said, the dataset consists of only 300 records, which means that this task is challenging. So more data later on could definitely be useful. And some of the features were categorical, and I decided to one-hot encode these, which means that, for instance, a categorical value between 0 and 3 becomes four binary features, where, for instance, a 0 would become 1, 0, 0, 0. This helps the model significantly during training, which we will see. I also normalized the data to prevent some features from overpowering other features during training. And for data visualization, I have used a correlation plot, and I've also used principal component analysis. So first of all, from the correlation plot, it became apparent that fasting blood sugar, that means the FPS feature, was extremely lowly correlated with the label. The correlation was about 0.2%, so this feature would only introduce noise to the model during training. So I decided to remove that feature. And from the principal component analysis, I could project the data onto the first two principal components and then plot this projection. And here we can see in the graph down below that the data is not completely linearly separable. So we will likely need to use some kernel tricks and nonlinear models to solve this issue. I also decided to add a bias term, which is of course crucial if you want to have good model performance. And over to the performance indicators, my main performance indicator of choice has been test accuracy, since I've really prioritized accuracy over anything else. And I want to point out that since this is a small data set, it has been crucial to use cross-validation when evaluating the models to give them a fair evaluation. So I've used tenfold cross-validation and applied it to all the 8 different models. I've used test accuracy since it's a metric that can be applied to all models, and it's very intuitive to understand what it means. And then in the end, I selected the model with the highest test accuracy. But of course, while tuning the parameters and hyperparameters and evaluating the models, I've also used other metrics such as the loss function for deep learning, which you can see here up to the right. And I've also used F1 score and confidence intervals to compare the models. And lastly, when it came to model selection, the result from the tenfold cross-validation was that the support vector machine with the second degree polynomial kernel worked best with an accuracy of 83%, which I would say, as I said earlier, is pretty good given the low amount of data points. And it's also worth noting that without using one-hot encoding, performance dropped by about 2%. And without scaling the data or normalizing the data, I mean, performance dropped by 1%. And this could mean a huge difference. Consider, for example, if 1 million users are using this service, if 3% of more of them are misclassified, a lot of people will suffer in vain. Sounds a bit dramatic, but that's the way it is. So, and here I have also visualized the support vector machine or an example of it. So if we were to use a linear kernel, which obviously would not work since we saw earlier that the data is not linearly separable, we would only have a straight line like this as a decision boundary. But with our polynomial kernel, we instead have a curved line, which proved to significantly boost the performance. So that was it for me. Thank you for listening to my presentation. Bye.